Let us try to understand what equilibrium is through a simple observation. Look at the closed container with a small amount of liquid bromine. What do you observe? You observe that some of the liquid bromine is evaporating to an orange vapor, and slowly the vapor becoming thicker. After some time, you can see that there is no change in the intensity of the vapor anymore, and also that a small amount of liquid bromine is left in the flask. How do you explain this? Here's the explanation. All the molecules in a liquid do not have the same kinetic energy. Some molecules at the surface of the liquid that possesses a relatively higher kinetic energy escape from the surface into the vapor phase. When the air inside the container is saturated with vapor, the molecules in the vapor phase condense to liquid as fast as the liquid evaporates. After some time, the number of molecules evaporating from the surface in a given time becomes equal to the number of molecules condensing on the surface during the same time. At this stage, equilibrium is said to have been established between the liquid and the vapor phase. This is why we see that the color of the vapor in the flask does not change. Thus, equilibrium may be defined as a condition in which two opposing tendencies balance one another. The equilibrium of liquid bromine with its vapor may be represented as Br2 liquid in equilibrium with Br2 gas. The pair of half-headed arrows indicates that the two processes, evaporation and condensation, are occurring simultaneously. At equilibrium, the rate at which the particles move from the liquid to the vapor phase will equal the rate at which the particles move from the vapor phase to the liquid. In this situation, the concentration of the vapor particles in the air space will be constant even though there is movement in both the directions. This equilibrium is, therefore, known as dynamic equilibrium. The opposing tendencies of a reversible change continue to take place with equal rates simultaneously at the equilibrium stage also. Hence, the equilibrium is called dynamic equilibrium. Equilibrium can be established for both physical and chemical processes. At the equilibrium state, if there is a change in the physical state, the equilibrium is called physical equilibrium. The important aspects of equilibrium involving physical processes can be understood by studying some phase transformation processes, such as solid-liquid, liquid-vapor, solid-vapor. Let's see solid-liquid equilibrium. Ice in equilibrium with water in a perfectly insulated thermos flask at 273 Kelvin and at atmospheric pressure stands as a perfect example of solid-liquid equilibrium. For this equilibrium, you can see that the temperatures as well as the masses of ice and water remain constant. Why is this so? Ice-water equilibrium is a dynamic equilibrium, where the number of molecules going from ice into water and the number of molecules going from water into ice are equal. As the rates of transfer of molecules from water to ice and from ice to water are equal, there is no change in the masses of ice and water. Since the system is insulated, no exchange of heat between the system and the surroundings is possible, and hence, the temperature remains constant. The equilibrium for this phase change may be written as H2OS in equilibrium with H2OL. It is important to note that ice exists in equilibrium with water only at a particular temperature and pressure. Thus, for any pure substance at atmospheric pressure, the temperature at which the solid and liquid are at equilibrium is called the normal melting point or normal freezing point of the substance. Let's now look at liquid-vapor equilibrium. Water in equilibrium with vapor in a closed vessel serves as a classic example of liquid-vapor equilibrium. Let's understand this through a simple experiment. A small amount of water is taken in a closed vessel to which a manometer is attached and left undisturbed for some time. After some time, you can see the slow increase of the mercury level in the manometer and the final attainment of a constant value. Did you also observe that there is a decrease in the volume of water in the vessel? How do you explain this? In the beginning, there was no water vapor inside the vessel. As water evaporated, the pressure inside the vessel increased, which was indicated through the rise in the level of mercury in the manometer. After some time, the level of mercury in the manometer remains constant, indicating that a state of equilibrium has been attained between water and water vapor. The molecules of the vapor in their movement collide with other molecules, with the walls of the container as well as the surface of the liquid. When some of the molecules with less kinetic energy come closer to the liquid surface, they get attracted to the surface. This process is called condensation. At any given temperature, evaporation and condensation take place simultaneously. After some time, the rate of evaporation becomes equal to the rate of condensation, and then liquid-vapor equilibrium is established. The pressure exerted by vapor over a liquid when it is in equilibrium with the liquid at a given temperature is termed as the vapor pressure of the liquid at that temperature. Water exists in equilibrium with its vapor at atmospheric pressure in a closed vessel. Thus, for any pure liquid at 1 atmospheric pressure, the temperature at which the liquid and vapor are in equilibrium is called the normal boiling point of the liquid. Let's look at solid-vapor equilibrium now. Some solid substances directly undergo a phase change from solid to vapor without the intermediate liquid state. This is called sublimation. Observe the solid iodine placed inside the conical flask and fitted with a cork. You can see the vessel getting filled up slowly with violet vapors. Have you observed that the intensity of the color has become constant? At this stage, we can say that an equilibrium state has been attained for the system. At equilibrium, the solid iodine sublimes to give iodine vapor, and the iodine vapor condenses to give solid iodine. The equilibrium can be represented as I2 solid in equilibrium with I2 vapor. You have learned that during physical process like phase transformation, it is possible to attain equilibrium. Similarly, when a physical process like dissolution is taking place, it is possible to achieve a state of equilibrium. There are two types of dissolution: gas in liquids and solid in liquids. Sugar in water is a classic example of solid in liquid equilibrium. First, sugar is added to a glass of water and stirred. It dissolves, forming a sugar solution. Then, as more and more sugar is added, it initially dissolves, but eventually reaches a stage where no matter how long you wait or how vigorously you stir, the sugar does not dissolve. The solution thus obtained is said to be saturated at the given temperature. Thus, at a given temperature, a solution that remains in contact with excess solute is said to be a saturated solution. In a saturated solution, a dynamic equilibrium exists between the solute particles in undissolved state and the solute particles in the solution. When the solution is kept in a closed system, the concentration of the solution and the amount of undissolved solute remains constant in the solution. The dynamic nature of this equilibrium can be established using radioactive sugar. Let's see how. Take a beaker containing saturated sugar solution. To this, add a small quantity of radioactive sugar and let the solution remain undisturbed for some time. Then check the solution for radioactivity. It is noticed that both the undissolved sugar as well as the solution has turned radioactive. This is a result of dynamic equilibrium, where the molecules of the radioactive and the non-radioactive sugar from the solid and liquid phases are being exchanged. This proves that there is dynamic equilibrium when a solid is dissolved in a liquid. Now let's look at the equilibrium involving the dissolution of gases in liquids. Have you ever wondered why soda fizzes when opened? The fizz that bubbles up when you open a soda water bottle is carbon dioxide gas. The phenomenon of fizz you see in carbonated beverages is due to the difference in the solubility of carbon dioxide at different pressures. At a given pressure, equilibrium exists between the carbon dioxide molecules in the gaseous state and those in the dissolved state in the liquid. This equilibrium is governed by Henry's law, which states the mass of a gas dissolved in a given amount of a liquid at any temperature is directly proportional to the pressure of the gas present in equilibrium with the liquid. All carbonated drinks are bottled under pressure to increase the solubility of carbon dioxide in the solution. When the bottle is opened, the pressure above the solution decreases. To reach the new equilibrium condition under decreased pressure, some of the dissolved carbon dioxide escapes. This gives rise to the fizz that you see when you open a bottle of carbonated drink. This is also the reason why the taste of carbonated drinks turns flat when the bottle is kept open for some time. Thus, we can summarize the general characteristics of equilibrium in physical processes as: at atmospheric pressure, a solid exists in equilibrium with a liquid only at one temperature, which is called its melting point. For example, at atmospheric pressure, ice exists in equilibrium at 273 Kelvin. At a given temperature, vapor pressure remains constant for liquid-vapor equilibrium. For example, in equilibrium between water and water vapor, the vapor pressure of water remains constant at a given temperature. At a given temperature, solubility remains constant for the dissolution of solids in liquids. For example, at the given temperature, the solubility of sugar remains constant in a given liquid. At a given temperature, the concentration of a gas in a liquid is directly proportional to the pressure of the gas over the liquid. For example, the concentration of carbon dioxide in water at equilibrium is directly proportional to the pressure of the gas over the liquid. At a given temperature, equilibrium can only be achieved in a closed system. For example, no equilibrium is attained when water in a beaker is kept open to the atmosphere. This is because the rate of condensation is much less than the rate of evaporation. At equilibrium, both the opposing tendencies occur at the same rate, and hence, a dynamic yet stable status is established. For example, for water at a given temperature in a closed vessel at equilibrium, the rate of evaporation is equal to the rate of condensation. At a given temperature, the attainment of equilibrium for a physical process is characterized by a constant value of one of its parameters, such as vapor pressure, melting point, solubility or concentration. For example, during equilibrium between liquid and gaseous water molecules, the vapor pressure of water remains constant at a given temperature. At equilibrium, all the measurable properties of the system remain constant. For example, for the solubility of solids in liquids, the solubility remains constant at a given temperature. Equilibrium in chemical processes, called chemical equilibrium, is the most important characteristic of irreversible reactions. The characteristics of chemical equilibrium can be understood only when you are familiar with certain terms, like reversible reactions and forward and backward reactions. So, let's get acquainted with these terms first. In general, the transformation of one substance into another is known as a chemical reaction. The chemical substances used at the initial stage during such transformation are called reactants, and the final chemical substances formed as a result of the chemical reaction are known as products. A reversible reaction may be defined as a chemical change in which the products can be converted back into the original reactants under suitable conditions. In a reversible reaction, The reaction in which the reactants react to give the products is called the forward reaction, while the reaction in which the products react back to give the reactants is called the backward reaction. Depending on the chemical nature of the products and the reaction conditions, the products formed may or may not react to give the initial substances. Let's take the example of the decomposition of calcium carbonate to demonstrate a reversible reaction. When calcium carbonate is heated strongly, it decomposes to form calcium oxide and carbon dioxide gas. When this decomposition is carried out in an open vessel, carbon dioxide, being a gas, escapes. Hence, there is no possibility for the products calcium oxide and carbon dioxide to react and give back the reactant calcium carbonate. Thus, the reaction proceeds in the forward direction only. Thus, the reactions whose products cannot be converted back into the reactants are known as irreversible reactions. When the same reaction of the decomposition of calcium carbonate is carried out in a closed vessel, the products, calcium oxide and carbon dioxide, combine to give solid calcium carbonate back. This clearly indicates that the reaction is capable of occurring in both the forward and the backward directions under favorable conditions. Such a reaction is called a reversible reaction. Reversible reactions are represented by a pair of half-headed arrows. If we plot a graph of a reversible reaction, we will notice that the rate of forward reaction is initially high. With the passage of time, the reactants deplete and the products accumulate. This leads to a decrease in the rate of the forward reaction and an increase in the rate of the backward reaction. After some time, a stage is reached when the rates of both the forward and the backward reactions becomes equal and the system reaches a state of equilibrium. We can graphically represent dynamic or chemical equilibrium as a forward reaction starting at a higher rate and a reverse process starting at zero rate coming together to reach an equilibrium point. Hence, when a reversible reaction is carried out in a closed vessel, a state is reached when the rate of the forward reaction becomes equal to the rate of the backward reaction. This stage is known as chemical equilibrium. It must be noted that the reaction can reach a state of equilibrium even if we start with the products, which is because equilibrium can be reached from either direction. The dynamic nature of chemical equilibrium can be understood by studying a gas phase chemical reaction. For example, when hydrogen and iodine are heated in a closed vessel, they react to form hydrogen iodide. When a mixture of equal initial concentrations of hydrogen and iodine are taken in a flask, maintained at 717 Kelvin, the intensity of the purple color decreases after some time. This is because, as the reaction proceeds, the concentrations of hydrogen and iodine decreases as they are consumed, and hence, the rate of forward reaction slows down. On the other hand, the concentration of hydrogen iodide increases with the progress of the reaction. As hydrogen iodide accumulates, the backward reaction of hydrogen iodide decomposing to hydrogen and iodine becomes significant. A stage is reached when the rates of the forward and backward reactions become equal, and the system is said to have attained equilibrium. At equilibrium, the concentrations of all the three species become constant. The graph depicts the variations of the concentrations of hydrogen, iodine, and hydrogen iodide as a function of time. You have already learned that in a reversible reaction, the reaction can reach a state of equilibrium even if we start with the products. Hence, the same state of equilibrium can be reached even if we start with hydrogen iodide alone. In this case, the concentration of hydrogen iodide will decrease and the concentrations of hydrogen and iodine will increase until they become constant at equilibrium. The attainment of equilibrium from either side can be shown in the form of a graph. The dynamic nature of the chemical equilibrium can be established by using radioactive iodine. When a small quantity of radioactive iodine is introduced into the above reaction in the state of equilibrium, it is found that the hydrogen iodide in the mixture contains radioactive iodine. This obviously shows that the reaction, though apparently standstill, is proceeding in both the directions. That is, the equilibrium is a dynamic equilibrium. Hence, the characteristics of chemical equilibrium are: equilibrium state can be approached from both the sides. The equilibrium is a dynamic equilibrium as both the forward and the backward reactions continue to take place with the same speed. At equilibrium state, properties such as pressure, concentration, density, or color remain unchanged over time. Equilibrium is possible only in a closed system. Consider the reversible reaction of nitrogen and hydrogen gases coming together to form ammonia. Is there any way to predict the extent of this reaction? Can we predict the direction of this reaction at any stage? Can we determine the equilibrium concentration from the initial concentrations for this reaction? These questions can be answered with the help of the equilibrium constant for that reaction. So, let's learn about equilibrium constant and its applications. In 1864, on the basis of experimental studies of many reversible reactions, two Norwegian chemists, Gilberg and Wag, established a relationship between the rate of chemical reaction and the concentration of the reactants and formulated the law of mass action. According to this law, at any instant, the rate of a chemical reaction at a given temperature is directly proportional to the active masses of the reactants at that instant. The term active masses in present times refers to molar concentration. In the early days of chemistry, concentration was called active mass. Hence, this law is known as the law of mass action. Let's see how it applies to the equilibrium state of a reversible reaction occurring in a homogeneous system at a given temperature. Let 1 mole of A react with 1 mole of B to produce 1 mole each of C and D. According to the law of mass action, the rate of forward reaction will be proportional to the molar concentration of the reactants A and B. That is, the rate of forward reaction Rf is directly proportional to the concentration of the reactants A and B. Or Rf is equal to Kf multiplied by the product of the concentrations of A and B, where Kf is the rate constant of forward reaction. Similarly, the rate of backward reaction will be proportional to the molar concentration of the products. That is, Rb is proportional to the product of the concentrations of the products C and D. Or Rb is equal to Kb multiplied by the product of the concentrations of C and D, where Kb is the rate constant of backward reaction. At equilibrium, the rate of forward reaction becomes equal to the rate of backward reaction. That is, Kf multiplied by the product of concentrations of reactants A and B is equal to Kb multiplied by the product of the concentrations of C and D. Or, this can be written as the product of the concentrations of products C and D divided by the product of the concentrations of reactants A and B is equal to Kf divided by Kb, which is equal to a constant Kc. Here, Kc is called the equilibrium constant of the reaction and is defined as the ratio of the product of the molar concentrations of the products to that of the reactants. The subscript C indicates that Kc is expressed in moles per liter. In the case that you just saw, the stoichiometric coefficients of the reactants and the products are unity. Now, let's consider a more general reaction of the type AA plus BB in equilibrium with CC plus DD, where A and B represent the stoichiometric coefficients of the reactants A and B, and C and D represent the stoichiometric coefficients of the products C and D, respectively. On applying the law of mass action, the rate of such a reaction is proportional to the concentration of each species raised to a power equal to the stoichiometric coefficient of the reaction. It, therefore, follows that at equilibrium, Kf multiplied by the product of the concentration of the reactants A raised to the power of A and B raised to the power of B is equal to Kb multiplied by the product of the concentration of the products C raised to the power of C and D raised to the power of D. This can be written as Kf divided by Kb is equal to the product of the concentrations of the products C raised to the power of C and D raised to the power of D divided by the product of the concentrations of the reactants A raised to the power of A and B raised to the power of B. This is equal to equilibrium constant Kc. Hence, the product of the concentrations of the reaction products raised to their respective stoichiometric coefficients in the balanced chemical equation, divided by the product of the concentrations of the reactants raised to their respective stoichiometric coefficients, has a constant value at a given temperature. This is known as equilibrium law or the law of chemical equilibrium. The equilibrium constant for the backward reaction is the inverse of the equilibrium constant for the forward reaction. Let us prove this with an example. Consider the reversible reaction of hydrogen and iodine combining to form hydrogen iodide. The equilibrium constant for this reaction is written as Kc equal to the concentration of the product, hydrogen iodide, raised to the power of 2 divided by the product of the concentrations of the reactants, hydrogen and iodine. Let us say this is equal to x. Now, the equilibrium constant for the reverse reaction, hydrogen iodide disintegrating to form hydrogen and iodine, is written as K-C is equal to the product of the concentration of hydrogen and iodine divided by the concentration of hydrogen iodide raised to the power of 2. Now, this is nothing but the reciprocal of x, which is equal to 1 by Kc. Thus, the equilibrium constant for the backward reaction is the reverse of the equilibrium constant for the forward reaction Kc. Chemical equilibrium may be classified into homogeneous equilibrium and heterogeneous equilibrium. The equilibrium in a system with all the reactants and products in the same phase is known as homogeneous equilibrium. Examples of homogeneous equilibrium include the reaction between hydrogen and iodine to form hydrogen iodide, the reaction between nitrogen and hydrogen to form ammonia, the hydrolysis of ethyl acetate to acetic acid and ethyl alcohol. This example represents homogeneous equilibrium in the liquid phase. The equilibrium in a system which has more than one phase is called the heterogeneous equilibrium. Examples of heterogeneous equilibrium include the thermal decomposition of calcium carbonate into calcium oxide and carbon dioxide, the displacement reaction between zinc and copper sulfate to give copper and zinc sulfate, the equilibrium constant in gaseous systems. For gases at constant temperature, the pressure of the gas is proportional to its concentration. Hence, for a reversible reaction involving gases, the equilibrium constant is conveniently expressed in terms of partial pressures of the reactants and products in place of molar concentrations. Let us now see how the pressure of a gas at constant temperature is proportional to its concentration. According to the ideal gas equation, PV is equal to nRT, or P is equal to nRT by V, where P is the pressure, N is the number of moles of the gas, V is the volume of the gas, R is the universal gas constant, and T is the absolute temperature. However, we know that N by V corresponds to molar concentration C. Therefore, the equation can be written as P is equal to CRT. Since R is constant, it can be written as at constant temperature, the pressure of a gas is proportional to its concentration. The equilibrium constant in terms of partial pressure is represented by Kp. Let us examine the relationship between the two equilibrium constants, Kc and Kp. For a general reaction of the type AA plus Bb in equilibrium with Cc plus Dd, the equilibrium constant is written as Kc is equal to the product of the concentration of the products C raised to the power of C and D raised to the power of D respectively, divided by the product of the concentration of the reactants A raised to the power of A and B raised to the power of B respectively. Now, if the reactants and products are gaseous, partial pressure may be used instead of concentrations. Then, the equilibrium constant in terms of partial pressure can be written as Kp is equal to the product of partial pressures of the products C raised to the power of C and D raised to the power of D respectively, divided by the product of the partial pressure of reactants A raised to the power of A and B raised to the power of B respectively. Since P is equal to CRT, it can be written as partial pressure of Pc is equal to the concentration of C multiplied by the product of R and T. Partial pressure of Pd is equal to the concentration of D multiplied by the product of R and T. Partial pressure of Pa is equal to the concentration of A multiplied by the product of R and T. Partial pressure of Pb is equal to the concentration of B multiplied by the product of R and T. Therefore, the equilibrium constant in terms of concentration can be written as Kp is equal to the product of concentration of the products C raised to the power of C, the concentration of D raised to the power of D multiplied by the product of R and T raised to the power of C plus D divided by the product of the concentrations of the reactants A raised to the power of A and B raised to the power of B multiplied by the product of R and T raised to the power of A plus B. This can be written as the product of the concentration of the products C raised to the power of C and D raised to the power of D divided by the product of the concentration of A raised to the power of A and B raised to the power of B multiplied by the product of R and T raised to the power of sum of C and D minus sum of A and B. This becomes equal to the product of the concentration of C raised to the power of C and the concentration of D raised to the power of D divided by the concentration of A raised to the power of A and the concentration of B raised to the power of B multiplied by the product of R and T raised to the power of delta N. Since the product of the concentration of C raised to the power of C and the concentration of D raised to the power of D divided by the concentration of A raised to the power of A and the concentration of B raised to the power of B is equal to equilibrium constant Kc. This can be written as Kp is equal to Kc multiplied by the product of R and T raised to the power of delta N, where delta N is equal to the number of moles of gaseous products minus the number of moles of gaseous reactants. Thus, Kc and Kp are related to each other by the equation Kp is equal to Kc multiplied by the product of R and T raised to the power of delta N. Let us see how the relationship between Kp and Kc varies with the difference in the number of moles of products and reactants. Case 1. When delta N is equal to 0. Consider the reversible reaction of hydrogen and iodine that gives hydrogen iodide. For this reaction, the difference in the number of moles, delta N, is equal to number of moles of hydrogen iodide minus number of moles of hydrogen and iodine, which is equal to 2 minus 2 is equal to 0. Substituting the value of delta N in the equation, Kp is equal to Kc multiplied by the product of R and T raised to the power of delta N. We get Kp is equal to Kc. Thus, for reactions in which delta N is equal to 0, the two equilibrium constants Kp and Kc are equal. Case 2. When delta N is negative. Consider the reversible reaction between nitrogen and hydrogen that gives ammonia. The difference in the number of moles for this reaction, delta N, is equal to number of moles of ammonia minus number of moles of nitrogen and hydrogen is equal to 2 minus 4 is equal to minus 2. Substituting the value of delta N in the equation, Kp is equal to Kc multiplied by the product of Rt raised to the power of delta N. We get Kp is equal to Kc multiplied by the product of R and T raised to the power of minus 2. Therefore, for reactions in which delta N is negative, that is, where the number of moles of gaseous products is less than the number of moles of gaseous reactants, Kp is less than Kc. Case 3. When delta N is positive. Consider the dissociation of phosphorus pentachloride into phosphorus trichloride and chlorine. For this reaction, the difference in the number of moles, delta N, is equal to number of moles of phosphorus trichloride and chlorine minus number of moles of phosphorus pentachloride is equal to 2 minus 1 is equal to 1. Substituting the value of delta N in the equation, Kp is equal to Kc multiplied by the product of R and T raised to the power of delta N. We get Kp is equal to Kc multiplied by the product of R and T raised to the power of 1. Therefore, for reactions in which delta N is positive, that is, where the number of moles of gaseous products is more than the number of moles of gaseous reactants, Kp is greater than Kc. You have already learned that the equilibrium in a system having two or more phases is known as heterogeneous equilibrium. Heterogeneous equilibria often involve pure solids or liquids. The concentration of these solids or liquids remains constant and does not change. Hence, while writing the equilibrium expressions for heterogeneous equilibria involving a pure liquid or a pure solid, the concentrations of these substances are excluded. Consider the thermal decomposition of calcium carbonate in a closed vessel. Solid calcium carbonate decomposes on heating into solid calcium oxide and gaseous carbon dioxide. The equilibrium constant for this reaction can be written as Kc is equal to the product of the concentrations of calcium oxide and carbon dioxide divided by concentration of calcium carbonate. Since calcium carbonate and calcium oxide are solids, their concentrations remain constant, and hence their concentration terms in the expression for equilibrium constant can be ignored. Now, the modified equilibrium constant for the system becomes Kc dash is equal to concentration of carbon dioxide, or Kp is equal to pressure of carbon dioxide. This expression clearly shows that at a particular temperature, irrespective of the masses of the two solids, calcium oxide and calcium carbonate, there is a constant concentration or pressure of carbon dioxide in equilibrium with calcium oxide and calcium carbonate. It has been found experimentally that the pressure of carbon dioxide in equilibrium with calcium oxide and calcium carbonate at 1073 Kelvin is equal to 2.5 into 10 raised to the power 4 Pascal. Hence, the equilibrium constant at 1073 Kelvin, which is equal to the pressure of carbon dioxide, is equal to 2.5 into 10 raised to the power 4 Pascal. Some characteristics of equilibrium constant are: the value of equilibrium constant is independent of the initial concentrations of the reactants and products. For example, the equilibrium constant for the reversible reaction of gaseous hydrogen and gaseous iodine in a sealed reaction vessel, irrespective of the initial concentrations at 731 Kelvin, is 46.4. The equilibrium constant for a particular reaction at a particular temperature is always constant and changes only with a change in temperature. For example, the equilibrium constant for the reaction of 1 mole of gaseous nitrogen and 3 moles of hydrogen combining reversibly to form 2 moles of gaseous ammonia at 298 Kelvin is 6.8 into 10 raised to the power 5. At 400 Kelvin, it is 41. And at 500 Kelvin, it is 3.6 into 10 raised to the power minus 2. The equilibrium constants of a forward reaction and its backward reaction are reciprocals of each other. For example, the equilibrium constant for the reversible reaction of gaseous hydrogen and gaseous iodine to form gaseous hydrogen iodide at 731 Kelvin is 46.4. The equilibrium constant for the reverse reaction of the decomposition of hydrogen iodide at the same temperature is the inverse of the equilibrium constant for the forward reaction of the formation of hydrogen iodide from hydrogen and iodine. This is equal to 1 by 46.4. If a chemical equation is multiplied by a certain factor, then its equilibrium constant must be raised to a power equal to that factor in order to obtain the equilibrium constant for the new reaction. For example, the reaction of nitric oxide and oxygen to form nitrogen dioxide may be written in two equivalent ways. The first way of writing it is 1 mole of gaseous nitric oxide and half a mole of gaseous oxygen combining reversibly to form 1 mole of gaseous nitrogen dioxide. The second way of writing it is 2 moles of gaseous nitric oxide and 1 mole of gaseous oxygen combining reversibly to form 2 moles of gaseous nitrogen dioxide. The equilibrium constant for the reaction of 1 mole of gaseous nitric oxide and half a mole of gaseous oxygen combining reversibly to form 1 mole of gaseous nitric oxide may be written as Kp is equal to concentration of nitrogen dioxide divided by the product of the concentrations of nitric oxide and oxygen raised to the power of half is equal to, say, x. the equilibrium constant for the reaction of 2 moles of gaseous nitric oxide and 1 mole of gaseous oxygen combining reversibly to form 2 moles of gaseous nitrogen dioxide may be written as Kp dash is equal to concentration of nitrogen dioxide raised to the power of 2 divided by the product of the concentrations of nitric oxide raised to the power of 2 and concentration of oxygen is equal to Kp square, which is equal to x square. Thus, you can say that the equilibrium constant for the second reaction Kp dash is equal to the square of the equilibrium constant of the first reaction. Given in the table are the equilibrium constant at various temperatures for the gaseous reaction of sulfur dioxide and oxygen to form sulfur trioxide. Can we guess at what temperature the reaction almost goes to completion? Can we predict the direction of the reaction at the given temperature? Can we calculate the equilibrium concentrations for this reaction? Let us see if equilibrium constant helps us in answering these questions. The knowledge of equilibrium constant helps us in predicting the extent of a reaction, predicting the direction of a reaction, calculating the equilibrium concentrations. Let us discuss each application in detail to appreciate the importance of equilibrium constant in a reaction. Predicting the extent of a reaction. The magnitude of equilibrium constant provides a useful indication of the extent of a chemical reaction. You have seen that the equilibrium constant for a reversible reaction is equal to the product of the concentrations of the products raised to their respective stoichiometric coefficients divided by the product of the concentrations of the reactants raised to their respective stoichiometric coefficients. As the products appear in the numerator and the reactants in the denominator of the expression, you can see that the magnitude of equilibrium constant is directly proportional to the concentrations of the products and inversely proportional to the concentrations of the reactants. Hence, a large value of an equilibrium constant indicates a high proportion of products to reactants, and vice versa. The magnitude of equilibrium constant, Kc or Kp, indicates the extent to which a reaction will proceed. If the numerical value of equilibrium constant is greater than 10 raised to the power 3, it means that the reaction nearly proceeds to completion and that the equilibrium concentration of the products is large. For example, the equilibrium constant for the gaseous reaction between hydrogen and chlorine to form hydrogen chloride at 300 Kelvin has a very large value of 4 into 10 raised to the power 31. If the numerical value of equilibrium constant is less than 10 raised to the power minus 3, it means that the reaction rarely proceeds, and also that the equilibrium concentration of the reactants is large. For example, for the gaseous reaction of nitrogen and oxygen reacting to form nitric oxide at 298 Kelvin, the equilibrium constant has a small value of 4.8 into 10 to the power of minus 31. If the numerical value of equilibrium constant lies between 10 raised to the power minus 3 and 10 raised to the power 3, it means that appreciable concentrations of the reactants as well as the products are present. For example, the equilibrium constant for the gaseous reaction of hydrogen and iodine combining to form hydrogen iodide at 700 Kelvin has a value of 57. The dependence of the extent of a reaction on its equilibrium constant can be illustrated as shown here. Let us now look how equilibrium constant helps in predicting the direction of a reaction. This is done by comparing the reaction quotient QC with the equilibrium constant Kc. So, for predicting the direction of a reaction, you also need to have knowledge of the reaction quotient. Let us first learn what reaction quotient is. At any point in a reversible reaction, the ratio of the concentration of the products raised to their respective stoichiometric coefficients to that of the reactants raised to their respective stoichiometric coefficients is known as the reaction quotient. QC with for molar concentrations and QP with for partial pressures. The reaction quotient expression of a reaction has the same equation as the equilibrium constant expression for that reaction. However, it is important to note that the reaction quotient is calculated using the concentrations or pressures at a given point of time in the reaction, and not the equilibrium concentrations or pressures. For a general reaction of the type A moles of reactant A and B moles of reactant B, reacting to give C moles of reactant C and D moles of reactant D. The reaction quotient QC is expressed as the product of concentration of C raised to the power of C and concentration of D raised to the power of D divided by the product of concentrations of A raised to the power of A and concentration of B raised to the power of B. Remember that the concentrations of the reactants and the products expressed in the equation are current concentrations and not equilibrium concentrations. Let us now examine how reaction quotient and equilibrium constant help us in predicting the direction of a reaction. If the value of reaction quotient QC is greater than equilibrium constant Kc, it means that backward reaction takes place. In other words, the reaction proceeds in the direction of the reactants. If the value of reaction quotient QC is less than equilibrium constant Kc, it means that forward reaction takes place. That is, the reaction proceeds in the direction of the products. If the value of reaction quotient QC is equal to equilibrium constant Kc, then it indicates that the reaction mixture is at equilibrium. Thus, we can predict the direction of a reaction with the help of its reaction quotient and equilibrium constant. For example, the equilibrium constant for the gaseous reaction of hydrogen with iodine to form hydrogen iodide at 731 Kelvin is 46.4. Suppose at a given time, the molar concentration of hydrogen is 0.2 m. That of iodine is 0.4 m, and that of hydrogen iodide is 0.8 m. The reaction quotient QC at this stage of the reaction is equal to the concentration of hydrogen iodide raised to the power of 2 divided by the product of the concentrations of hydrogen and iodine. This is equal to 0.8 square divided by 0.2 into 0.4. The value of the reaction quotient comes out to be 8.0. As the value of the reaction quotient is smaller than the equilibrium constant, the reaction proceeds in the forward direction. It means that more of gaseous hydrogen and iodine react to form the product hydrogen iodide. Let us now look at how equilibrium constant helps in calculating equilibrium concentrations. For this, let's consider a problem. Mix 2 moles of hydrogen and 3 moles of iodine together in a 1-liter closed vessel. It attains equilibrium at 440 Kelvin. Calculate the composition of the mixture at equilibrium given that the value of Kc for the reaction at 440 Kelvin is 0.02. The first step in calculating equilibrium concentrations involves writing a balanced equation for the reaction, like this. The second step is to set up a table describing the initial concentration, change in concentration on going to equilibrium and equilibrium concentration. The second step can be easily remembered in the form of ICE chart, where I stands for the initial concentrations or pressures for each species in the reaction mixture. C represents the change in the concentrations or pressures for each species as the system moves towards equilibrium. E represents the equilibrium concentrations or pressures of each species when the system is in a state of equilibrium. In constructing the table, use X to show the change in concentrations of the species. Use the stoichiometry of the reaction to determine the concentrations of the other substances in terms of X. The ICE chart for the given problem is: the initial concentrations of hydrogen and iodine in the reaction mixture are 2 moles and 3 moles respectively, while it is 0 for hydrogen iodide as it is not present at the beginning of the reaction. Let X moles of hydrogen and X moles of iodine combine to give 2X moles of hydrogen iodide as shown in the balanced equation. At equilibrium, the concentrations of hydrogen, iodine and hydrogen iodide will be 2 minus X, 3 minus X and 2X respectively. In the third step, substitute the equilibrium concentrations in the equilibrium equation and solve for X. The equilibrium equation for the reaction is Kc is equal to concentration of hydrogen iodide raised to the power of 2 divided by the product of the concentrations of hydrogen and iodine. On substituting the equilibrium concentrations and the value of the equilibrium constant in the equation, we get 2x square divided by 2 minus x multiplied by 3 minus x is equal to 0.02. This is equal to 4x square divided by x square minus 5x plus 6. This can be written as 4x square divided by x square minus 5x plus 6 is equal to 2 divided by 100. On cross multiplying, we get 100 multiplied by 4x square is equal to 2 multiplied by x square minus 5x plus 6. On crossing off 100 with 2, we get 50 multiplied by 4x square is equal to x square minus 5x plus 6. This becomes equal to 200x square is equal to x square minus 5x plus 6. This equation can be written as 200x square minus x square minus 5x plus 6 is equal to 0. This becomes equal to 200x square minus x square plus 5x minus 6 is equal to 0. This is equal to 199x square plus 5x minus 6 is equal to 0. This is in the form of a quadratic equation. ax square plus bx plus c is equal to 0. In this equation, a is equal to 199, b is equal to 5 and c is equal to minus 6. In order to solve x, you must use the formula x is equal to minus b plus or minus square root of b square minus 4ac divided by 2a. On substituting the values of a, b and c in the quadratic equation, we get minus 5 plus or minus square root of 5 square minus 4 multiplied by 199 multiplied by minus 6 divided by 2 multiplied by 199. This can be written as minus 5 plus or minus square root of 25 plus 4,776 divided by 398. This can be further written as minus 5 plus or minus square root of 4,801 divided by 398. The square root of 4,801 is 69.28. Hence, the equation can be written as minus 5 plus or minus 69.28 divided by 398. This can be written in two forms. One form is x is equal to minus 5 plus 69.28 divided by 398, which is equal to 0.160. The other form is x is equal to minus 5 minus 69.28 divided by 398. This becomes equal to minus 74.28 divided by 398, which is equal to minus 0.186. As concentration cannot have a negative value, it is clear that the correct value of x is 0.160. The fourth step is to calculate the equilibrium concentrations from the value of x. The initial number of moles of hydrogen is 2. Hence, at equilibrium, the concentration of hydrogen will be 2 minus 0.160. This is equal to 1.84 moles per liter. In the case of iodine, the initial number of moles were 3, and hence, the equilibrium concentration would be 3 minus 0.160. This is equal to 2.84 moles per liter. And finally, the equilibrium concentration of hydrogen iodide will be equal to 2 multiplied by 0.160. This is equal to 0.32 moles per liter. Step 5. Check your results by substituting them in the equilibrium equation. On substituting the concentrations of hydrogen, iodine, and hydrogen iodide in the equilibrium equation, we get Kc is equal to 0.32 square divided by 1.84 multiplied by 2.84. On solving this, we get the value of the equilibrium constant as 0.02. This is the same as the given value. Hence, the equilibrium concentrations are correct. According to thermodynamics, the knowledge of the sign and magnitude of the free energy change of a chemical reaction allows us to predict its spontaneity at constant temperature and pressure. The change in the Gibbs energy of a chemical reaction can be defined as the difference in the Gibbs energy of the products and that of the reactants. This can be represented as delta G is equal to G of products minus G of reactants. When delta G is equal to 0, it means that the Gibbs energy of the products is equal to the Gibbs energy of the reactants. At this stage, the system is said to have achieved equilibrium. When delta G is positive, it means that the Gibbs energy of the products is greater than the Gibbs energy of the reactants. Hence, the reaction is considered non-spontaneous and proceeds in the backward direction. In other words, the products are converted back into the reactants. When delta G is negative, it means that the Gibbs energy of the products is less than the Gibbs energy of the reactants. This, in turn, means that the reaction can proceed spontaneously with the accomplishment of the network. In other words, the reaction proceeds in the forward direction of formation of the products. Let us now examine the relationship between the equilibrium constant and Gibbs energy. Consider a general reversible reaction, reactants A and B, in equilibrium with C and D. The change in the Gibbs energy of a reaction in which all the reactants and products are in the standard state is known as standard Gibbs energy change, which is represented by delta G naught. The relationship between Gibbs energy change, delta G, and standard Gibbs energy change, delta G naught, is given as delta G is equal to delta G naught plus RT ln Q, where R is the universal constant, T is absolute temperature, and Q is reaction quotient. Since the reaction quotient Q for the reaction is equal to product of the concentrations of the products C and D divided by the product of the concentrations of the reactants A and B, the equation can be written as delta G is equal to delta G naught plus RT ln product of concentrations of products C and D divided by product of concentrations of reactants A and B. At equilibrium, when delta G is equal to 0 and Q is equal to equilibrium constant Kc, the equation becomes delta G is equal to delta G naught plus RT ln Kc is equal to 0. This can be written as delta G naught is equal to minus RT ln Kc, or ln Kc is equal to minus delta G naught divided by RT. Taking antilog on both the sides, we get Kc is equal to e to the power minus delta G naught divided by RT. The reaction spontaneity in terms of the value of delta G naught can be known by using the equation Kc is equal to e to the power of minus delta G naught divided by RT. If delta G naught is less than 0, then the term minus delta G naught divided by RT becomes positive, and the value of e to the power of minus delta G naught divided by RT becomes greater than 1. This makes Kc greater than 1. It means that the reaction is spontaneous. Or, that the equilibrium composition strongly favors the products. In other words, the reaction proceeds in the forward direction to such an extent that it almost goes to completion. If delta G is greater than 0, then the term minus delta G naught divided by RT becomes negative, and the value of e to the power of minus delta G naught divided by RT becomes less than 1. This makes Kc less than 1. This means that the reaction is not spontaneous, or that the equilibrium composition favors the reactants. In other words, the reaction proceeds in the forward direction to a very little extent, and only a minute quantity of products is formed. Have you ever wondered why mountaineers carry oxygen cylinders with them while climbing high mountains? You know that hemoglobin, a protein containing iron in the red blood corpuscles of blood, is responsible for the transport of the oxygen to the cells. When human beings or animals inhale oxygen from the atmosphere, it combines with hemoglobin in the blood and forms oxyhemoglobin. Equilibrium exists between oxygen and hemoglobin, which can be represented as Hb plus O2 in equilibrium with HbO2, where Hb stands for hemoglobin. A healthy equilibrium is maintained as long as there is sufficient oxygen in the air. At high altitudes, the air pressure decreases, and it becomes difficult to obtain the oxygen needed. This results in a shift of the equilibrium to the left, away from the oxygenated hemoglobin. Due to the insufficient supply of oxygen to the body's cells and tissues, a person tends to feel lightheaded. Therefore, to shift the equilibrium to the right, towards oxygen, pressurized oxygen has to be introduced from an oxygen tank. Hence, mountaineers carry oxygen cylinders with them when they climb high mountains. Thus, we can say that if a system at equilibrium is subjected to a change in the concentration in one of the substances, then it no longer remains at equilibrium, and the equilibrium position shifts in the direction in which this change is reduced or nullified. A change in temperature or pressure may also alter the equilibrium. This is the application of an important generalization, known as Le Chatelier's principle. The effect of temperature, pressure, and concentration on a reversible reaction in equilibrium was predicted qualitatively by Le Chatelier. He gave a principle which is now known as Le Chatelier's principle. Le Chatelier's principle may be stated as: if a system at equilibrium is subjected to a change in the temperature, pressure, or concentration of the reactants or the products that govern the equilibrium, then the equilibrium position shifts in the direction in which this change is reduced or nullified. The factors that influence equilibrium are concentration, pressure, and temperature. Let us learn about the effect of each factor in detail. When a system at equilibrium is disturbed by the addition or removal of any reactant or product, Le Chatelier's principle predicts that the position of equilibrium shifts in the direction in which this change is reduced or nullified. the effect of change in the concentration of the products and reactants can be readily known through an experiment. In a beaker, take 20 ml aqueous solution of 0.2 molar iron 3 nitrate. It is pale yellow in color. When 5 ml aqueous solution of 0.002 molar potassium thiocyanate is added to it, the color of the solution changes from pale yellow to red. This is due to the formation of thiocyanate iron 3 ions. The intensity of the red color becomes constant after some time, which indicates the attainment of equilibrium. The equilibrium mixture contains aqueous Fe plus 3 ions, aqueous SCN- ions, and aqueous FeSCN plus 2 ions. The equilibrium constant, Kc, for this reaction can be written as Kc is equal to concentration of FeSCN plus 2 divided by the product of concentrations of Fe plus 3 and SCN-. You have already learned that at equilibrium, reaction quotient Qc becomes equal to equilibrium constant Kc. Hence, you can write Qc is equal to Kc at equilibrium. To understand the effect of change in concentration on equilibrium, let us consider some cases. Adding the reactants Fe plus 3 or SCN- ions to the equilibrium mixture. Removing the reactants Fe plus 3 or SCN- ions from the equilibrium mixture. Adding the product FeSCN plus 2 ions to the equilibrium mixture. Removing the product FeSCN plus 2 ions from the equilibrium mixture. Case 1. Adding the reactants Fe plus 3 or SCN- ions to the equilibrium mixture. Suppose you add a few ml of a solution containing soluble Fe plus 3 or SCN- ions to the equilibrium mixture. You can see that the color of the solution becomes darker. The reaction quotient at this stage of the reaction is given by Qc is equal to concentration of FeSCN plus 2 divided by the product of concentration of Fe plus 3 and SCN- ions. On the addition of Fe plus 3 or SCN- ions to the equilibrium mixture, the denominator value in the expression for reaction quotient increases. This results in a decrease in the value of the reaction quotient. Now, the value of Qc becomes less than Kc. You have already studied that when Qc is less than Kc, the reaction proceeds in the direction of formation of products. That means the reaction proceeds towards the formation of FeSCN plus 2 ions. This is the reason why the solution becomes dark on the addition of more Fe plus 3 or SCN- ions. Hence, in general, we can say that increasing the concentration of any one of the reactants always favors the forward reaction. Case 2. Removing the reactants Fe plus 3 or SCN- ions from the equilibrium mixture. Now, suppose you add a few ml of oxalic acid to the reaction mixture at equilibrium. You can see that the intensity of the red color of the solution decreases and the solution turns pale. Why does this happen? Oxalic acid reacts with Fe+3 ions in the equilibrium mixture and forms a stable complex trioxalate ferrate 3 ion. Due to this, there is a decrease in the concentration of free Fe+3 ions in the solution. This results in a decrease in the denominator value in the expression for reaction quotient. Thus, the value of QC becomes greater than Kc. When Qc is greater than Kc, the reaction proceeds in backward direction. Hence, FeSCN plus 2 ions undergo dissociation to give Fe+3 and SCN minus ions. Due to the decrease in the concentration of FeSCN plus 2, the intensity of the red color decreases. Thus, we can conclude that removing or decreasing the concentration of any one of the reactants always favors the backward reaction. Case 3. Adding the product FeSCN plus 2 complex ions to the equilibrium mixture. On adding FeSCN plus 2 complex ions to the reaction mixture, the value of the numerator increases in the expression for reaction quotient. Thus, you can say that adding a product to the equilibrium mixture results in the backward reaction. This results in Qc becoming greater than Kc. Hence, the backward reaction, that is, the dissociation of FeSCN plus 2 ions into Fe+3 and SCN minus ions, takes place. Case 4. Removing the product FeSCN plus 2 ions from the equilibrium mixture. On removing FeSCN plus 2 ions from the equilibrium mixture, the value of the numerator in the equation for reaction quotient decreases. This results in Qc becoming less than Kc. Hence, the forward reaction of Fe+3 and SCN minus ions combining to give FeSCN plus 2 takes place. Thus, you can conclude that removing a product from the equilibrium mixture results in the forward reaction. From the experiment, we can summarize that the addition of reactants or the removal of products favors the forward reaction, while the removal of reactants or the addition of products favors backward reaction. The ability to predict the effect of change in concentration has great commercial application in the cases of reactions where the product is a gas or a volatile substance. Here are 2 examples. In the manufacture of ammonia by Haber's process, high yield of ammonia is favored by the addition of the reactants nitrogen or hydrogen, or the removal of the product ammonia from the reaction mixture. In the large-scale production of calcium oxide, which is used as an important building material from calcium carbonate, carbon dioxide is constantly removed from the kiln, which drives the reaction to completion. Let us now study the effect of pressure change on a system at equilibrium. According to the Le Chatelier's principle, when a system at equilibrium is subjected to change in pressure, then the system tends to shift the equilibrium position in such a direction that the effect is nullified. You know that the pressure of a gas is directly proportional to number of moles of the gas. Hence, the effect of pressure can be easily understood by considering the change in the number of moles between the products and the reactants. This can be made clear by studying three cases. Case 1. When the number of moles of the reactants is greater than the number of moles of the products. Case 2. When the number of moles of the products is greater than the number of moles of reactants. Case 3. When the number of moles of the reactants is equal to the number of moles of the products. Case 1. When the number of moles of the reactants is greater than the number of moles of the products. Consider the gas phase reaction N2 plus 3H2 in equilibrium with 2NH3. In this reaction, 4 moles of gaseous reactants, 1 mole of nitrogen and 3 moles of hydrogen become 2 moles of the gaseous product, ammonia. Suppose the equilibrium mixture is kept in a cylinder fitted with a piston at constant temperature and is compressed to 1/2 of its original volume. As the volume decreases to half, the pressure will be doubled according to the equation PV is equal to constant. As the pressure is doubled, according to Le Chatelier's principle, the equilibrium shifts in the direction of decrease in pressure or the number of moles of the gas. So, in this case, the reaction proceeds towards the formation of the product, ammonia. If you decrease the pressure on this equilibrium, the equilibrium shifts in the direction of the increase in the number of moles of the gas. Hence, ammonia undergoes dissociation to give back nitrogen and hydrogen. Case 2. When the number of moles of the products is greater than the number of moles of the reactants. Consider the gas phase reaction PCl5 in equilibrium with PCl3 and Cl2. What happens when pressure is increased on this equilibrium? In this reaction, the number of moles of gas increases in the forward direction. Hence, as the pressure increases, the equilibrium shifts in the backward direction, which involves fewer moles of gas. Case 3. When the number of moles of the reactants is equal to the number of moles of the products. Consider the gaseous reaction H2 plus I2 in equilibrium with HI. You can see that in this reaction, the number of moles of the reactants and the products are the same, which is 2. As there is no change in the number of moles of the products or the reactants, pressure does not have any effect on the equilibrium. The effect of pressure is important only on those equilibria that involve gaseous substances and not on equilibria that involve liquid and solid phases. This is because the volume and concentration of a solution or liquid is almost independent of pressure. For example, pressure has no effect on the equilibrium reaction between solid zinc and aqueous copper sulfate to give zinc sulfate and copper, which involves only solid and liquid phases. Now, here is an interesting question for you. Does the addition of an inert gas into a gas phase equilibrium at constant volume result in a shift in the equilibrium? If the volume is kept constant and an inert gas, such as helium or argon that does not take part in the reaction is added, then the equilibrium remains undisturbed. This is because the addition of a non-reactive gas does not change the partial pressure of the other gases in the container.